everybody and welcome to this video. My name is Cliona. I'm a H1 chemistry student and today I'm going to be taking you through the solution to question 7 from the 2021 Leaving Cert paper. Now this question is based on acids, bases and pH calculations. So let's start off with question A. Okay, so in question A, part 1, we're asked to define an acid according to, and part 1 is the theory of Arrhenius, and part 2 is a theory of Brønsted-Lowry. Okay, so these are just definitions that you should know. The first one, the definition of an acid according to Arrhenius, is that an acid is a substance which dissociates in water to produce H plus ions, okay? And if you replaced H plus ions with protons here, you would still get your marks, okay? So this question will give you 4 marks in total. You'll get 2 marks here for saying that it dissociates in water or suggesting that it dissociates in an aqueous solution. And you'll get your other 2 marks for saying that it produces H plus ions or protons. So now for the second part of this question, which is asking us to define an acid according to the theory of Brønsted and Lowry, all you need to say is that an acid is a proton donor, okay? So an acid is a proton donor and a base is a proton acceptor in terms of the definition of an acid according to Brønsted and Lowry. And for just saying that an acid is a proton donor, you're going to get 4 marks in this question. Okay, so now we're going to move on to question part 3 in A, and this asks us to state one limitation of Arrhenius's acid-base theory, okay? So if you just remember from the question above, Arrhenius's definition is that an acid is a substance which dissociates in water or aqueous solution to produce H plus ions, okay? So there's a good few limitations, but the limitation that I always learned for this, because it's simple enough, because it's in the definition that I learned off, is that it's confined to aqueous solutions only, okay? So you can see in the question, it says that it dissociates in water, okay? Or aqueous solutions. So if it can't dissociate in aqueous solution, or if it's not, say, a liquid, then it's not really applicable to the Arrhenius acid-base theory, okay? So for this question, you are going to get 6 marks, okay? So water must always be involved, so that is a limitation. So now let's move on to question part 4 of A, the last part of A. So this asks us, what is a conjugate acid-base pair in Brønsted-Lowry theory, okay? And you can remember again, Brønsted-Lowry theory of an acid is that an acid is a proton donor and a base is a proton acceptor. So a conjugate acid-base pair in this theory is an acid and a base which differ by 1 proton. Okay, so the base accepts the proton to become the conjugate acid, and the acid donates the proton to become the conjugate base. Okay, so they differ by 1 proton. And for this question, you will get 3 marks. So now we're going to move on to question B. So in question B, it's just the one part and it asks us to distinguish between a strong acid and a weak acid. And when it tells us to distinguish, you really need to say a line for both, okay? So between a strong acid and a weak acid, again, there's a few ways to distinguish between them. But my go-to line is that a strong acid is a good proton donor. Because we know that an acid is a proton donor and a strong acid is a good proton donor. Whereas, and this is my favorite word to use when we're asked to distinguish, okay? Because that's your halfway line. That's saying you've kind of defined the first part. Now you're going to define the second part to distinguish between them. So then, whereas a weak acid is a poor proton donor, okay? So you're going to get 3 marks for the first part of this question, saying what a strong acid is, and you're going to get 3 marks for the second part of this question, where you say what a weak acid is, okay? So altogether there, you're going to get 6 marks for question B. Okay, now let's move on to question C. Okay, so question B tells us that sulfuric acid is a strong dibasic acid, and we're asked to write a balanced equation to show that the conjugate base of H2SO4, which is sulfuric acid, acts as a Brønsted-Lowry acid in water. So if it acts as a Brønsted-Lowry acid in water, what does that mean? It means that it is going to donate a proton. Okay, so it asks us to show that the conjugate base of H2SO4. So let's see. What is the conjugate base of H2SO4? So if it's asking us for a conjugate base, H2SO4 is an acid. We know it is because we're told that it's sulfuric acid. But, so if it's an acid and it wants to become its conjugate base, what does that have to do? It has to donate a proton or get rid of a proton, okay? So if it gets rid of a proton, we're going to be left with H, only one H, SO4, okay? And it's going to have a negative charge because it's just lost a proton. It's just lost a H plus ion, okay? So it's negative charge. So that is the conjugate base of H2SO4. Okay, so now we need to show that this conjugate base acts as a Brønsted-Lowry acid in water, okay? So we're going to get HSO4 minus, okay, plus water, okay? And we're going to use our equilibrium signs because we always use those when we're dealing with acid and base equations, okay? In this particular question, you wouldn't have lost any marks if you didn't use these, but in the following question, you would. So it's just always best to use these. Okay, so we need to show that it acts as an acid. So it donates a proton. So it donates another proton. So we're left with SO4, 2 minus, okay, because it's going to get another negative charge, plus, this is going to gain the proton, so H3O plus. Okay, so you're going to get 3 marks for doing that. And then you're going to get your other 3 for balancing it, okay? So let's see, what do we have? We have hydrogen, we have sulfur, and we have oxygen, okay? So right-hand side, left-hand side, just do a little table for yourself. Okay, how many hydrogens have we got on the right-hand side and the left-hand side? So on the right-hand side, we have 1, 2, 3. On the left-hand side, we also have 3, so that's all good. Sulfur, on the right-hand side we have 1, on the left-hand side we have 1. Oxygen, on the right-hand side we have 5. And on the left-hand side we also have 5, okay? So we're all good. It's balanced, okay? So you just get another 3 marks for that. So all together here, you would have got 6 marks. Okay, so now we're going to move on to question D. Okay, so question D, part 1, asks us to write a balanced equation to show the dissociation into ions in water of a weak monobasic acid represented by HA. Okay, so that's our weak monobasic acid, and that is going to dissociate in water. So we have HA plus H2O. Okay, what's it going to turn into here? So it's an acid, so it's going to donate a proton. So we're going to be left with A minus plus H3O plus. Yeah? And again, just balance it. Just make sure it's balanced. So we just have H, we have A, and we have O. So on the right-hand side, we have 3 H's. Left-hand side, we also have 3 A's. We have 1 on either side. And O's, again, we have 1 on either side. Okay, so that's all good. So you get 3 marks here for the equation or the formula, and 3 marks here to just make sure it's balanced. So 6 marks altogether. So now let's move on to question 2. Okay, so I've just put question part 2 and 3 together. Okay, just because they're very related here. So we're told that if HA, okay, is 1.5% dissociated in a 0.1 molar solution, part 2 asks us to find the concentrations of H3O plus ion and A minus ion in moles per litre in the solution. Okay, so this sounds a lot more complicated than it actually is. Okay, so the dissociation of HA on the right hand side of our weak monobasic acid is going to equal the concentration of both H3O plus and A minus on the right hand side, okay? Because it dissociates into those 2 on the right hand side. So all we need to do is, so that is, it's 1.5% dissociated in a 0.1 molar solution. So for part 2, all we need to do is find 1.5% of 0.1. Okay, so how do we do this? We go 0.1 multiplied by 0.015, okay? And that gives us 3/2000. And that is moles per litre. You can write it in scientific notation if you'd prefer, but when I see a fraction like this, it just makes a bit more sense to me. It's just personal preference, okay? So they're both the same, so I'm just going to write the concentration of H3O plus is equal to the concentration of A minus is equal to 3/2000 moles per litre, and that can just be represented as M. Okay, so now we're going to move on to the third part of question D. And this asks us to calculate the pH of the 0.1 molar HA solution. Okay, so when we're calculating the pH, what formula are we going to use? We're going to use this one, which we should learn off, okay? pH is equal to minus log to the base 10 multiplied by the molarity of H plus ions in the equation. This can also be written as minus log to the base 10 by the molarity of H3O plus ions. Okay, so what do we have? In this question, we have the molarity of the H3O plus ions, which is 3 over 2,000 moles per litre, which we found in question D part 2, just above there, okay? And just to mention as well, D part 2, that's 6 marks in total. I forgot to put it in there. Okay, so to find the pH of the 0.1 molar HA solution, we need to put into our calculators minus log to the base 10 multiplied by 3 all over 2,000. Okay, so now let's just put that into our calculator. And that gives us a pH value of 2.82. Okay, so in this question, you would have got 3 marks for stating the pH, how to find a pH, the kind of formula there, minus log to the base 10 of H3O plus, okay? And then you would get your other 3 marks for getting the correct answer. So 6 marks in total for question D, part 3. So now let's move on to the final part of question 7. Okay, so in this question we are told, hence or otherwise, calculate the value of the acid dissociation constant, Ka for H of A, assuming ionization does not alter the concentration of the non-ionized form, i.e. take HA is equal to 0.1 molars after dissociation. Okay, this is another formula that I personally did learn off for the Leaving Cert. When you're finding the acid dissociation constant Ka, I use this formula, okay? So Ka is equal to, so you're looking for what the acid has dissociated into. And in this case, it is H3O plus, these are just what's on the right hand side, okay? Multiplied by, so I'm just going to bring those down a bit. So H3O plus the molarity of that multiplied by the molarity of A minus, which is also on the right hand side, all over the molarity of HA, which is the weak monobasic acid, which we're trying to find the value of the acid dissociation constant for. Okay, so this is simple enough now. We know the molarity of H3O plus and A minus from part D part 2 to be 3 over 2,000 moles per litre. Okay, so 3 over 2,000 for H3O plus and the same for A minus. And we're told the molarity of HA to be 0.1. Okay, so now let's just work out the value of Ka by just popping this into our calculator. And that gives us a value, and this is in scientific notation, which is perfectly fine, of 2.25 multiplied by 10 to the power of minus 5. Okay, so Ka is equal to 2.25 multiplied by 10 to the power of minus 5. And you're going to get 6 marks for that. Okay guys, so that is all for this question. I hope that you found this video helpful and that it might have cleared up any problems that you may have had going through this acid, base and pH calculations question. Thanks very much for watching and I'll see you in the next video.